Welcome everyone to today's webinar. I will start in a couple of minutes. I just have to manually let some people join here. For those who are already here, welcome and thank you for participating. A few just hints from my side. So all participants will be muted. If you have questions or if you have some remarks, please be so kind and type them into the chat or use the chat function. There will be a discussion after the presentation. For those who facing issues regarding sound or video, don't worry, you will get an automated link by mail to download the video of the webinar. So there will be a recording and the recording will be available to all participants and will be sent afterwards. I also have to apologize because the Tuesday session that had or was scheduled for Tuesday will take place next Tuesday because this week we had some issues with Corona and COVID here in the company, so we had to cancel it and shift it to next week. So I'm sorry for that. For those who want to join again, or for those who are missing the Tuesday webinar, that was due to the COVID issues here in the company. So we will repeat this on next Tuesday morning, 10 o'clock in European time zone. There are still some people joining, so let's just give them a chance to take part, and then I can start. For all the others, today's topic will be hydrogen technologies and thermal analysis, a little overview about current hydrogen research and what we can do with thermal analysis regarding the hydrogen topic. It's the same webinar we did already in spring, and as said, it will be held today and also on next Tuesday. Okay. Meanwhile, I should have managed to let everybody in who was requesting. So again, welcome from my side. I will repeat, the webinar will go as follows. You will all be muted. You can type remarks and questions into the chat. We will have a short discussion after the presentation. And after the webinar, you will get an email link to be able to download the video and the recording of today's webinar session for those who are missing something or who joined later. I will start with the presentation now. So again, welcome everyone. As mentioned, today's topic will be hydrogen technology and thermal analysis. I first want to introduce myself. My name is Sebastian Seibt. I'm the head of laboratory in our application laboratory here in our headquarters in Selb in Germany. I'm a chemist and I joined Linzais in 2013. You can get in touch with me directly using this mail address s.seibt@linzais.de in case you have questions regarding the webinar series or in case you have questions regarding some test or application measurements. For all of you who do not know the company, Linzais Messgeräte GmbH in Germany was founded in 1956 by Dr. Maximilian Linzais, which is visible on the top left picture. He was a physicist. He moved to Selb in Bavaria and founded his own company here. In the meantime, we are owned by his son, Mr. Klaus Linzais, and his two sons. So the third generation, Mr. Florian Linzais and Dr. Vincent Linzais, are our CEOs, while Florian Linzais is doing the management and the overall CEO daily business, while Vincent Linzais is more or less managing the research and development. Besides our headquarters in Germany, we have facilities in the US, India, and China, where we have our own locations, our own buildings, and our own offices to be able to maintenance our instruments from all over the world. In all these locations, you will find service technicians, sales agents, and of course, people from the service and technical stuff. But the manufacturing takes place in Germany only. In all the other countries that are not, with the benefit of Linzais subsidiary, in all the other countries, there are distributors and free agents who are representing us quite well since the very beginning. So in almost every country, there is a company representing us, or we are represented by ourselves. Our main business area is the manufacturing of thermal analysis instruments, also thermal conductivity and thermoelectric analyzers. And of course, we offer measurements in our own laboratories, which are located in, as said, US, China, and mainly Selb in Germany. Our product range, I just mentioned it, can be seen here. We cover the complete range from differential scanning calorimetry in different variations, over thermogravimetric analyzers to the combined simultaneous thermal analyzers, the classical simultaneous thermal analyzers, which consists of a thermobalance and a DSC. Besides that, we have many dilatometers to measure expansion and coefficient of thermal expansion, the so-called CTE, and also thermomechanical analysis, which is thermal expansion shrinkage measurements and stress and strain experiments, so thermomechanical analysis in general. This is what I would call the classical thermal analysis. Besides that, we have a lot of instruments to investigate thermal conductivity and thermal diffusivity, starting at the laser flash technique, but also hot wire techniques and guarded hot plate like heat flow meters or TIM testers for transinterface materials. We also miniaturize this for thin films and have various thin film analyzers to be able to measure layers and coatings, which is getting more and more important. And also we build instruments for the analysis of thermoelectric effect, like the Hall effect, the Seebeck coefficient, electrical resistivity, charge carrier concentration, stuff like that. That's also, I would say, meanwhile, it's a known field in thermal analysis that we cover with different instruments. And also this is done in microscale or with microsamples meanwhile, as the focus is clearly on the chip industries, computer techniques, and microscale. And finally, what makes Linzais a little bit different than all the other companies, we do a lot of customizations. That means we do a lot of high pressure modifications and also high temperature modifications where we use tungsten and graphite furnaces, where we use pressure vessels to be able to reach several hundred bars, to be able to customize any kind of instrument that you see here according to the customer needs. We can couple the instruments to other techniques like evolved gas analysis with mass spectroscopy, infrared spectroscopy, and others, which is frequently asked by different research institutes or universities. And that's what makes Linzais a little bit different than the competition. So that's what we focus on also. Today's topic, to come back to this, the hydrogen technologies, is also something that is more or less a customization or modification, because most of the instruments I just showed you can be operated in hydrogen or partial hydrogen atmospheres if modified or if equipped properly. And this is a market that is growing and that we are aiming at more or less. So this is the reason why we do this presentation here the second time this year now. In contrast to the other webinar series where I present or where we usually present a certain technique or a certain instrument, this presentation is a little bit different because I structured it from the application side. So I will show you the current hydrogen research, the so-called roadmap, and then I will show you what or where the thermal analysis technique plays a role or comes into account. Therefore, I organized it like this. In 2020, the Fraunhofer Research Group in Germany published a strategic paper which showed the so-called hydrogen roadmap to transfer the fossil energy generation and the nuclear energy generation into renewable green energy. And they focused on where hydrogen technology could play a key role, or where are issues, where is some research needed and what's already existing. And I will just follow this map and guide you through it and explain a little bit what they found and what is actually going on in research and where the thermal analysis can be involved. So first of all, most of you should know that the German politics decided that they want to, more or less quickly replace fossil fuels, nuclear fuels by green energy, which means biomass, which means nuclear, no, not nuclear, of course, which means solar power plants, which means wind power plants and stuff like that. And the problem is electricity is pretty difficult to store in bigger amounts and for longer times. And therefore, the question is, if you want to transfer electrical energy into chemical energy to be able to store it, to be able to transport it, and if yes, what kind of chemical energy should be used? And one solution that was already present since a couple of decades now is, of course, the hydrogen. So this roadmap focuses on how to transform renewable energies into chemical bound energy, that means into hydrogen, how to store it, how to export it, how to transport it, how to retransform it into energy, either by mobile use or by stationary use, how to use it in industries or domestic, and then getting after that getting the water back for the next cycle for new electrolysis and new cycling. So the key issues would be how to produce it, how to store it, and how to transport it. In this paper where I'm more or less referring to, they separated the actual hydrogen research into the key research technologies or the key research topics, which is mainly the electrolysis. So the electrolysis is the process where hydrogen is usually generated. In the easiest way, you use electrical energy, apply it onto water, and then separate the water molecule into hydrogen and oxygen. This process is, of course, energy consuming, and then if done properly, you get a big amount of hydrogen out of that. The electrolysis can be optimized by using catalysts, by optimizing the cells themselves, and arrange them in arrays or arrange them in structures that get the maximum hydrogen output out of the minimum energy input. Do it directly where the energy is generated instead of doing it somewhere central, which also saves transport loss of energy and stuff like that. There's a lot of research regarding storage and pipelines, guaranteed production rates. Of course, if there's sun power or wind power used, then there's fluctuation. So there's focus on how to get a constant production ongoing. Is it useful to support the green energy by, I would say, classic energy techniques to have an ongoing production or not? What's the lifetime of those electrolysis cells, and how to optimize the used catalysts? Then the next field of the topic would be the hydrogen use in production in industries. For instance, using hydrogen as a replacement where fossil gases are usually used, like in steel production. Is it possible to replace them by hydrogen or not? What would be required to do so? What are the logistic solutions and logistic problems if you want to do stuff like that? Could you use hydrogen to form other fuels like ammonia or like other substances that can be formed out of hydrogen to be used as an engine for fuel or to be used as a mobile fuel? And that's what the industry topics usually are. Besides that, as a third point, we have traffic and mobility. So what's the difference and the different aspect if you want to use hydrogen in mobility? So storage conditions in a car or in a truck are different from a big tank for a power plant. So what's the problems and what's the possible solutions for mobile storage? And of course, the diffusion rates is a big topic here. How about on-site hydrogen generation? If you wanted to use hydrogen as a mobile fuel, is it useful or does it make sense to generate it on site? So store it as a different molecule and then release hydrogen on site instead of using hydrogen as a storing media. What kind of cooling techniques are needed for storage? Is cooling technique needed for storage? And stuff like that. Then, of course, if you want to use hydrogen as a fuel in an electric engine, there is a need of a fuel cell, and fuel cell is a topic, or is the big topic regarding traffic and mobility. So the optimization of fuel cells is a big topic, where also a lot of thermal analysis measurements takes place, by the way. And fuel cell production in general is something we'll focus on. And as a last field, there is the power generation. So the back transfer from chemically bound power into real electrical power, electrical energy. What is the loss rate? How can this be optimized? How can the hydrogen storage be integrated in national power networks? How can it be coupled with renewable energy concepts in general? So that's the research field that Fraunhofer Society defined, and that's what I'm sorting them by. And I will go through them one by one and give you some application examples where we are already involved from the perspective of thermal analysis. So first of all, we start with the hydrogen generation. We start with renewable energies. The so-called green energies are, as I mentioned, windmills, solar panels, geothermal plants, biomass. The goal is the reduction of carbon dioxide emission, of course, and also to try to reduce nuclear waste. And it's an alternative to gas and oil sources or resources. We have some customers, or we had some customers in the past who were manufacturing solar panels, silicon wafers for solar panels, organic solar cells, and we also had a customer who was producing windmill blades. Usually these blades consist of ultralight metals or ultralight compound materials, and some of these composite materials were measured by dilatometers in the past by us, where we determined the expansion rate or the expansion itself of these windmills when facing temperature changes due to wind, sunlight, and environmental influence. So we measured different materials, measured the coefficient of thermal expansion of different mixtures for them, and see slightly differences in expansion at different temperatures to make more or less get an idea about the material, because the structure itself should not break, should not get porous, or should not expand too much when facing temperature changes, when facing temperature fluctuations. And that's why these materials need to be described quite well and need to be understood well before being able to construct such big and long-lasting structures. So this is where we are already involved, and I also have measurements, but I'm not allowed to show them all, regarding solar panel cells, where we also did expansion measurements and where we also did some measurements regarding thermal conductivity in the past. So here we are already involved since many years regarding the material properties. The next step would be the transformation from the energy you get from the green sources into real chemical energy. So transformation of power or voltage into hydrogen. That's usually done by electrolysis. So as I mentioned before, it's quite a simple process. You just have to create a DC source, and DC source is of course not a battery, but in this case, the DC source is usually a windmill or solar panel. You couple it to electrolyte, so which is usually fed by water. This water is in touch with the anode and cathode, and once the voltage is flowing, the water is separated into hydrogen and oxygen. So it's dissolved in hydrogen and oxygen. This process is called electrolysis. It consumes a lot of energy, and at the end, it produces you two gases, oxygen on the one side and hydrogen on the other side. The oxygen, of course, in most cases is released to the atmosphere. The hydrogen is stored in tanks, is stored in bottles and pipes, wherever you want it. On the picture down here, you see a big electrolysis facility. By the way, here in the city where I'm living here in Selb, where Linsize is placed or located, close to us, there is a hydrogen research center where they have big electrolysis units running and where they do research for real industrial scale electrolysis machines and processes to be able to produce hydrogen in real big scale out of solar fields and out of big windmill parks. So we are quite close to the research already from the very beginning, just to mention that. Regarding this electrolysis process, as I said, they usually use catalysts to minimize the power that you need, and they use so the material of the cathodes and anodes is quite crucial. So usually you use platinum wires, you use platinum alloy wires for these cathodes and anodes. And what we also did in the past was expansion measurements and also measurements before of the cathodes to make sure that the thickness is not decreasing too much and too fast, because the cathodes and anodes are consumed by time and needs to be replaced. And this replacement or the need for replacement can be measured by thickness measurements, as well as the if you have cathodes and anodes that could be regenerated, you can also observe the regeneration process by measuring thickness, measuring the surface structures, and also measuring expansion and shrinkage of them. So you can check if they get porous, if they get brittle, if they expand, shrink by dilatometers and thermomechanical analysis. And what you see here is the expansion of platinum wires, which is some typical application, which is just as an example, but this is also possible with the cathode and anode material, which we also did, where you see shrinkage and expansion, where you can measure by dilatometer the thickness for before and after use, and where you can see if there's phase changes, if there's change in expansion, which would indicate that these cathodes and anodes needs to be replaced. So this is where we also are already involved. Another method to generate hydrogen besides direct electrolysis would also be the so-called coal gasification. In case you use biomass and charcoal-containing materials or carbon-containing materials as a source, you could gasify them by just using coal or using the biomass, putting it into a big furnace, and then fire it in the presence of water steam. You could also generate hydrogen out of water steam by using biomass and carbon. In contrast to just burning it, where you just generate heat and a lot of heat will be lost, you could directly transform the carbon that's more or less bound in here, of course, into carbon monoxide and carbon dioxide. But if you use water steam in this process, you could use this carbon to generate hydrogen. The advantage would be a lot more of your carbon that would be just burned off and wasted as heat could be used and be transformed into hydrogen that can be used for different processes. Additionally, you get other gases that can be used in industries like sulfur, carbon monoxide, carbon dioxide. You get gases and syngas mixtures that can be used in chemical industry, and you get hydrogen. So you do not lose that much energy in just heat that gets off, like if you just would burn it, but more or less you transfer it into chemical energy. This process of coal gasification is quite complex and depends on the real resource that you are using. So the raw material can be coal, it can be coke, it can be biomass, plant waste, depends. So depending on what you have, the process is a little bit different, and depending what you add, oxygen or water steam or whatever, the outcome is a little bit different. But the so-called coal gasification process is one process that our customized thermobalancers and our customized STA instruments can already handle since a couple of years now, and where we have a lot of customers. And this coal gasification process is one of the most applications that we handle. As you can see here in this diagram, this is a typical coal gasification process. So usually it's going like this. You heat the sample to a certain temperature. During the heat, you see the red curve. This is the mass change. So during the first heating, you see a loss of volatiles. All the stuff that goes directly into gas phase will be lost. You get rid of it. So the mass, the initial mass changes. During the first experiment step, you just heat up. You just generate a pressure. So usually these operations are done at a little overpressure. In this case, it was at 50 bar, inert gas atmosphere. And once you reach the target pressure and target temperature, water steam was added to the process. So from inert gas to water steam, once the water was applied on the sample started to react with the water. So the carbon reacted with the water to form carbon monoxide and hydrogen. The mass of the sample, of course, decreases, and the hydrogen formation starts up here until all the coal is consumed, and then you have hydrogen carbon monoxide. If you go on feeding with water steam, you get carbon dioxide out of this. And the hydrogen gas can easily be separated from the outgas. So this is what technically happens. Of course, in our thermal analyzer, we just analyze the process. We analyze process speed, transformation rates, and ideal pressure and temperature, and so on. In technical scale, of course, you would try to separate the gas and not optimize the conditions, because for optimizing conditions, that's why thermal analysis is used here. But this is one of the typical applications that we recently did. The next step in the hydrogen cycle after hydrogen generation would be storage and transport. The hydrogen storage is easier to achieve than the storage of electrical energy. There's less loss. And of course, for electrical energy storage, you need a big, or you would need a very, very big battery in big amounts. Such big batteries don't exist. It's not possible to build a battery that's big enough to empower a city or something like that. So for storage of electrical energy, there is a need of transferring it into chemical energy, which we just did within our hydrogen cycle here. For storing hydrogen, there are different options. First of all, of course, the easiest option is to put it into gas bottles, pressurized tanks, pressurized bottles. But hydrogen is a very small molecule and it diffuses out of everything. So therefore, using bottles and using tanks for big amounts goes with a certain risk that you have a lot of diffusion leakage and diffusion loss rates. And this can be dangerous if the hydrogen around your storage facilities reaches a critical concentration, because then it's flammable and then you're in a risk of explosion and fires. Therefore, there are different options. One, well known, is sorption. So there are materials like porous ceramic materials, porous metal surfaces like titanium powders or zeolite structures that can absorb hydrogen at a certain rate and amount. And when increased in temperature or pressure is decreased, the hydrogen can be desorbed again. So like a sponge, it absorbs the hydrogen and releases when squeezed, more or less. And besides that, there's the possibility of real chemical storage. So using the hydrogen to transfer it into another molecule that can be, in a reversive process, undone and then released again. So this is the options for storage usually that are available. In thermal analysis, the storage in gas bottles and tanks is more or less for short time and not interesting, because we do not investigate the gas phase and we do not investigate these bottles. What's more interesting for us and what we did in the past is sorption and desorption processes on zeolite structures, so-called metalloorganic frameworks or metal surfaces. We also did some experiments with customers that were working in hydrogen storage as a ammonia or as a methane gas. However, this is also gas phase analysis, which is usually not that topic in thermal analysis. Coming back to the first, so sorption on metalloorganic frameworks on titanium pellets is what we already did and what's quite easy to understand. You have a so-called metalloorganic framework, or MOF, that has a microstructure or nanostructure like here in this picture. So little holes and gaps and little pores where the hydrogen molecules can diffuse in. They then absorb at the inner surface within these pores. And once the pressure is released or reduced, or the temperature is increased, the binding or the affinity of hydrogen to the surface is reduced and the hydrogen will be released. When hydrogen with overpressure is again applied to the structure at lower temperatures, then it can be loaded again. So by controlling the pressure of hydrogen and controlling the temperature of these frameworks or metal structures or zeolite structures, hydrogen can be very safely stored and released. So that's quite a useful tool. The problem is that the capacity, so the volume of material you need for storing a significant amount of hydrogen, is quite high. So you need a high volume of metalloorganic framework, a high volume of MOF structure to be able to store high hydrogen volumes. And this is the key issue, because these high-tech structures are quite expensive. And then you again have a big storage tank. And this is something for longer term storage, however, only in lab scale or MIDI scale, but not industrial scale. So this is, for research exactly where we are aiming at, but not the big solution for industrial processes. We already did some experiments on that. So we had customers who were investigating hydrogen storage at catalyst surfaces, at metallic ionic frameworks, at titanium surface. That's what we did. In this example here, the absorption and desorption of hydrogen on a platinum aluminum catalyst surface was measured. This, in that case, was a heat flow measurement. So the heat absorption and the heat of desorption could be determined. So we do this by thermobalancers. We do this by calorimeters, so DSC techniques. This sorption and desorption process is a process where you can measure and detect the released or consumed energy as an enthalpic signal. If you put a piece of it into a DSC crucible and measure the heat flow, you see the amount of heat that's released during sorption and that's required for desorption. And by knowing this enthalpy, you can calculate how much temperature you would need to adsorb or desorb, and especially desorb, a decent amount of hydrogen. So that's what we did on the one hand. On the other hand, I'm not sure if this is in here. No, sorry, I will show it later. We did hydrogen storage on a titanium surface, titanium structure, where you just gravimetrically determined the amount of bound hydrogen by measuring the weight change of our superstructure when facing hydrogen under pressure. So how much weight gain do you see and how much weight loss do you see when the pressure is reduced? And that's also something what we did in the past quite frequently in this hydrogen field. Once the hydrogen is stored and we are able to handle it, we can go one step further, which is use it as a fuel, use it in industries, use it in technologies. So if you want to use hydrogen in a truck, car, or anywhere mobile, the controlled hydrogen release is the key issue. How to release it controlled, so by temperature control of desorption or by pressure control desorption, of course, or using a tank and then just use a valve and use the gaseous hydrogen as a gas doesing directly. That would also be possible. And then how to transfer it back into electrical energy. In hydrogen-driven buses, cars, and trucks, this is usually done by a so-called fuel cell. And as I said at the very beginning of this presentation, fuel cell technologies is a big, big topic where we are already very much involved because there's so much research, so much different types of fuel cells, and so many different approaches that there is a big field of research, which is very interesting for us. The fuel cell itself, you can see it on the picture, or you can see it on the schematic drawing on the slide here, is quite easy to explain. You have a membrane, and on the one side of the membrane, you feed it with hydrogen. On the other side, you feed it with oxygen. Usually, if you mix hydrogen and oxygen and then give it a little bit energy, it will ignite and it will immediately react heavily and form water. But I do not want to have an explosion or a fireball or whatever. I want to get the energy back transferred into electrical energy. Therefore, we have this electrical membrane, and it's like this. The hydrogen can diffuse through it, the oxygen can't. Therefore, the hydrogen goes into the membrane, goes into the inner surface where it meets the oxygen, and when reacting on the surface of this membrane, the water molecules are formed and are transported out of the fuel cell. By this process, the electrons that are not necessary and are released during this process can flow within this membrane in an electric circuit, and these electrons that flow into this electrical setup here generates the electrical voltage that I need. So I transfer the molecules back into water molecules and electrons. That's what the fuel cell more or less does. So this process directly uses the energy out of the reaction between hydrogen and oxygen, and directly you cannot get it even better. So you cannot optimize this. This is almost 100% transformation rate. You directly grab the electrons out of the process without them causing heat, causing pressure, causing something. You just form water. The water drops out here, and the electrons, the energy is directly consumed in the electric circuit. And that's what a fuel cell more or less does. Of course, the membranes themselves are high tech, and there are many different techniques. And you already should know, or maybe you know, that fuel cells can also work with different fuels than hydrogen. There are already fuel cell technologies existing where methanol or carbon monoxide or other gases are used. And the process is not always hydrogen and oxygen forms water. It can also be something different. Depending on the application, there are many fuel cell types out on the market. These letters over here are the names of different types of fuel cells. So they more or less common ones are the so-called PMFC and AFC fuel cells for hydrogen. They use an electrolyte liquid. They are filled with an electrolyte liquid between the membranes. Usually it's polymer structure, or it's potassium hydroxide structure, or dissolution. And you have membrane materials that are consisting of noble metals and non-noble metals, noble metal mixtures that act as a catalyst within the membrane. As said, this membrane technologies is quite high-tech research, and there are many different fuel cells on the market, and this is where a lot of research is going on. What we already did and what we do is we did a lot of measurements regarding thermal conductivity of these membrane materials, regarding electrical conductivity, electrical resistivity of membrane materials, measurement of heat flow of the electrolytes, and yeah, stuff like that. That's what we usually do by DEC, by STA, by thermoelectric analyzers, and that's where we are already involved, and we are or want to be involved in the future as well. What you see here is a measurement by a classical STA. So this is the controlled hydrogen released from a titanium hydride matrix. So we had titanium hydride. I'm sorry, this is a misspelling here. And the titanium first absorbed the hydrogen at elevated pressure. Then the pressure was released to room temperature. Then the sample was put into the thermal analyzer. Then it was heated. It was just heated at ambient pressure. And during heating, the hydrogen molecules that were adsorbed were then desorbed. You can see the mass change in the two-step desorption process, and you also can see the heat flow. You can see the heat consumption during the release. And out of this, you get exactly the temperature when it's desorbed and how much is desorbed, and also how much energy you exactly need. And this helps to optimize the process of controlled hydrogen release by desorption. The last point, besides mobile use of hydrogen as a fuel, is the use of hydrogen in industries. I mentioned before that in industries, it's more or less challenging to replace fossil fuels by hydrogen, because in steel industries, in the steel furnace or in the steel formation process, the fossil fuels usually comes with a certain amount of carbon. It forms, of course, also water, but also carbon monoxide, carbon dioxide in the process. If you replace it by hydrogen and fire the hydrogen, you will only have water but no carbon feeding anymore. So the steel itself behaves a little bit different. And this needs to be investigated and needs to be optimized. And another application that's quite interesting is metal sintering or additive manufacturing. This measurement you see here was a hydrogen sinter measurement performed on a vertical dilatometer, and it was powder sintering of metal powders in hydrogen atmosphere. A lot of sinter metal and additive manufacturing processes require inert atmospheres, or even, like in this case, reducing atmospheres. If you have a mixture of multiple metals and you want to melt them into an alloy or melt them into an additive, you have to make sure that they are not reacting with oxygen or residual oxygen in this process. Otherwise, you would have a mixture of metal oxides and metals. If you want to have a real alloy, oxygen-free, you need to somehow gather the oxygen out of the process, and sometimes also the hydrogen activates the surface of metals and therefore gives you a proper result or different result than the absence of hydrogen. Therefore, these sinterings or these sinter studies are frequently done in hydrogen atmosphere. And we did a lot of sinter measurements by dilatometer in absolute hydrogen atmosphere to optimize the sinter processes in additive manufacturing. This is something we do usually in inner atmosphere or oxygen-containing atmosphere for ceramics. And now it's the same technology that we use for ceramics. However, this is sinter optimization under 100% hydrogen atmosphere, where the metal or the metal powder is heated, and then at a certain temperature, the sintering starts, so the material starts to shrink at a certain rate until the final value is reached. The trick or the research purpose here is to find the right temperature, to find the right heating rate, to get the ideal process outcome. And this is what a lot of customers already are doing with us together. So this is also a typical application. The last point I want to highlight is when doing measurements in hydrogen atmosphere, safety is of course also in thermal analysis an issue. And whenever it comes to the use of hydrogen or flammable gases, then it requires some safety precautions. What we did here is we thought about it very carefully, and we finally designed a solution that is quite useful. We have a so-called hydrogen safety setup that can be modular equipped to all of our instruments to be able to operate our instruments safely under hydrogen atmosphere or under flammable atmospheres or under flammable gases. This unit consists of gas flow controllers, detector systems, and an automatical safety system that can shut down gas valves and flush with inert gas. It's connected to the gas inlets and outlets of the system, and it can automatically preparate atmospheres. That means you enter in the software what kind of atmospheres you want to use. The system evacuates the thermal analysis instrument, of course, the reaction chamber. It evacuates it, it fills it with inert gas, then it removes the inert gas and fills it with reactive atmosphere. Completely automatical. It purges out whatever you need. It uses the inert gas you want, and it generates the atmosphere that you define. There are vacuum level monitors that automatically check the vacuum level you reach during evacuation. It makes sure that there is no residual oxygen or an oxygen level that's fine before it fills in hydrogen or any other flammable gas. It measures deviations from the set values in case of leakage. In case of a gas container is running empty, it will automatically close the valves and purge with inert gas. It's coupled to detection systems that measure the hydrogen or methane or whatever you use concentration around the instrument at every connector, at every pipe. If there's a leakage detected, if there is a release to the room or unwanted release to the room, it will also shut down the gas flow and bring the instrument into a safe state. The big advantage is nobody needs to stand in front of the instrument. It will be operated completely automatical. The PC that controls it can stand anywhere. You do not need to sit next to it. You do not need to stand next to it. It can be additionally equipped with a burn-off unit. Usually the outgassing is going into a fume hood or is going into a controlled waste system. If that's not the case, if you're working in an industrial process hall or somewhere, it can be equipped with a burn-off unit. So the outgassings that come out of the instrument goes through a constant burning flame to make sure that all the flame gas that comes out of your instrument is burned off and not released to the environment. This picture here shows a big setup with a vacuum pump, with a safety system, with a multiple array gas dosing system, even with a humidity generator. So this is the maximum equipment that you can have with this blue hydrogen sensors and gas sensors equipped at the instrument, at the gas box, at the pipes. And this is the setup we usually offer. As said, it will detect empty gas cylinders. It will detect failure of burning units. It will detect even a power outage. It will make sure that nothing can happen. And this is what we developed, and this is what we advertise and what we sell with our instrument to be able to run under safe conditions. Because it reacts fast, it reacts automatical, and nobody needs to observe the instrument during the experiment all the time. It will be brought in a safe state in case there is something happening. And I would strongly recommend to use a configuration like this if you want to do such experiments, because once there's a leakage and there is hydrogen release and you have a hot furnace in the room or in the instrument, nobody should be needed to run to the instrument and push manually any kind of button, because then he's standing right in front of it, and that could end very poorly for the people and for the person who has to go there. So therefore, that's what we did, what we developed, and that's what I said, where Linsight is leading in customization of these kind of instruments and that kind of applications. There are some additional safety features I have to mention. We also have integrated timers to make sure that after some working hours, some parts are replaced or some parts are checked, like the inner tubes, like ceramic parts that could get thinner or could get consumed by hydrogen. We use special sealings, of course, and we have a set maintenance intervals that are automatically recorded and automatically displayed, and that's what it's the actual state of the art that we are actually offering. If somebody has more improvements or has safety issues that should be considered, we are always open for improvements at that point. Finally, this is where I want to end this presentation. This is what we do regarding measurements in hydrogen so far. We are always open to improve that any further. We are always open for hydrogen applications and new partnerships, because for us, that's a very, very important field, and that's a very interesting field. And yeah, that's the overview, and that's the point where we are standing at the moment. At this point, I want to thank you for your attention, and that's the end of my presentation now.